Hey guys, today we're going to be looking at our second lesson about exponents. We've already looked at how to multiply them. Now we're going to look at how to divide them. So when we look at our quotients of powers, remember a quotient is the answer to a division problem. And we want to see what 3 to the 5th over 3 squared means. So we have 3 times 3 times 3 times 3 times 3 all over 3 times 3. Well, remember, anything divided by itself is 1, so this 3 divided by 3 is 1, and this 3 divided by 3 is 1, which leaves me with 3 times 3 times 3 in the numerator, and I can rewrite that as just saying 3 to the power of 3. So we're going to look at it now with x's. So x to the 7th means x times itself 7 times. All over x cubed, which is x times itself 3 times. And again, anything divided by itself is 1. So this x divided by x is 1. This one is 1, as well as this one. Which leaves me with x times x times x times x in the numerator. So x to the power of 4. And we can look at x to the 10th over x to the 8th as well. So x to the 10th would be 10 x's. All over x to the 8th, which would be 8 x's. And I can simplify my 1s. So this will simplify to 1, 1, 1. Which leaves me with x times x in the numerator, which I can rewrite as x squared. I want you guys to take a look at the simplified answer and the original problem and come up with a hypothesis of what you think the rule might be. So go ahead and pause it, let your brain think a little bit, and unpause it whenever you're ready. Welcome back, you guys. I hope y'all are able to figure it out. Anytime we have exponents on the same base, so notice 3 to the 5th and 3 squared was the same base, x to the 7th and x cubed, we can actually subtract those exponents. So our rule will be when you divide the same bases, you subtract the exponents. And if you kind of think about it, if you look at this first example, you have 3 to the 5th, which means there's 5. Well, 3 is being multiplied by itself 5 times. So there's 5 3s in the numerator, and there's 2 in the denominator. So if you ask yourself who has more, that's going to be the numerator. And how many more? Well, that's 3. So 3 cubed would stay in the numerator. The same idea can be applied with x to the 7th over x cubed. The numerator has more x's, and it has 4 more x's. So x to the 4th will remain in the numerator. So our rule, if we have a to the power of m divided by, remember, same base, so a to the power of n, that's going to equal a to the power of m minus n. A to the power of m minus n. So let's look at our first couple of examples. We have a to the 5th times b to the 9th over a cubed times b cubed. There's nothing I can simplify in the numerator. There's nothing I can simplify in the denominator. So now I see that I have a to the 5th over a cubed, which gives me a to the power of 5 minus 3, and b to the 9th over b cubed, so b to the power of 9 minus 3, which simplifies to a squared b to the 6th. And again, if you look, a to the 5th and a cubed, there's more a's in the numerator, and there's 2 more. And then again, b to the 9th over b cubed, there's more b's in the top, so it's going to keep it. And there's 6 more, which leaves just a 1 in the denominator, which is equivalent to what we got earlier. When we look at 2, I can't simplify anything in the numerator, but I have a power raised to a power in my denominator. And remember from last class, when you have powers raised to a power, you multiply the exponents. So that 2 is going to kind of distribute in to the x squared and the y cubed. So that becomes x to the 7th, y to the 9th in the top still, and then x to the 4th, and then y to the 6th. And since I am dividing same bases, I'm subtracting my exponents. So I get x to the 7th minus 4, and then y to the 9th minus 6, simplifying to x cubed and then y cubed. And if you want to think about it in terms of the shortcut, kind of, when you look at your x's, your numerator has more, and it has 3 more. Who has more y's? Well, that's your numerator, and it has 3 more. So you're just left over 1, and again, that's equivalent. So now for this third one, we have the entire fraction being raised to the exponent, meaning that exponent is going to go to everything in the numerator and everything in the denominator. And our u in that denominator, I don't see an exponent, so I'm going to write in my understood 1, and I'm going to show my arrows, so I know that it goes to both of them. So powers raised to a power, that's when you multiply those exponents together. So I get u to the 4th, that looks like a w, u to the 4th, v to the 6th, over u squared, v to the 4th. And so now I have u to the power of 4 over u squared. And since those are the same bases, I'm going to subtract my exponents. So I have u to the 4th minus 2, and then v to the 6th minus 4, which simplifies to u squared v squared. And if we look at our shortcut, the numerator has more u's and it has 2 more. The numerator has more v's by 2, so 1 goes in that denominator. Again, they are equivalent. All right, guys, this next one you guys are going to love. If you plug in 7 to the power of 0 in your calculator, you're going to get a positive 1. If you plug in -2, and remember the negative has to be on the inside of the parentheses. If you plug that in to the power of 0, you get 1. And then x to the power of 0, well, you guessed it, it's going to be a 1. So then what do you think this next one is? I'm going to let you make a guess. So I'm going to let you pause it. Did you say 1? Because if you did, you forgot the cardinal rule. Exponents only go to what they're told to, which is in the parentheses. So while this right here becomes a positive 1, that negative in front of it actually makes it a -1. But this rule is going to be your favorite because anything to the power of 0 is equal to 1. Like I could give you the most crazy thing, like 1,200,000, well, oopsies, 1,200,000. A to the 4th, B to the 17th, C to the 27th. And if I put it all the way to 0, everything inside of this parentheses just becomes a positive 1. So we like this. We like this rule. So for our algebraic rule, we have a to the power of 0 is equal to 1. Super fun. All right, so let's look at this first example. We have our powers raised to a power, so it's going to multiply in. So I get a to the 8th, b to the 16th, over a to the 8th, b to the 8th. So when I go and I see the a to the 8th over a to the 8th, I can subtract. So I get a to to the power of 8 minus 8, and then b to the power of 16 minus 8. So I really have a to the power of 0 and b to the power of 8. But I know that anything to the power of 0 is 1, so I'm just going to say this is b to the power of 8. And if you think about it, anything divided by itself is 1. So right here, a to the 8th over a to the 8th would really become a big old 1. So let's look at 2. Again, powers raised to a power, so your exponents will multiply. This numerator becomes x to the 8th and y to the 12th over x to the 8th, y cubed, and then z cubed. Well, x to the 8th and x to the 8th right here is being divided by itself. And 8 minus 8 will give me a 0, so this is going to simplify to 1. And then I have y to the 12th in my numerator and y cubed in the denominator. So the numerator has more y's, so it's going to claim it, and it has 9 more. But then I see this z cubed, and I don't see any z's in the numerator, so I'm going to leave the z cubed in the denominator because there's nothing to cancel it out with. So I want you to take a moment and pause, and I want you to attempt number 3 on your own. Remember, if you don't see an exponent on a variable, it's an understood 1. And whenever you're ready, go ahead and unpause to see if you got it right. How did we do, guys? Did you make sure to do your outer exponent first? And then if you look, the denominator has more t's, and it has 2 more. There are no u's in the denominator, so u to the 5th will stay in the numerator. And then the denominator has more v's by 3, so v cubed will stay in the bottom. All right, on to our last example. Negative exponent rule. X cubed over x to the 7th. Well, if we use our subtraction rule, I know that that would be x to the 3rd minus 7, which tells us that's x to the power of negative 4. But if I do my expansion, that's x times x times x over x times itself 7 times. And remember, anything divided by itself simplifies to 1. So I'm left with a 1 in the numerator and x to the 4th in the denominator. Well, this and this are going to be the exact same thing, but we cannot have negative exponents. So what happens is if I have x to the negative 4, and right now it's kind of like it's over 1, this fraction bar acts like a magic eraser for negative exponents. So if it's a negative exponent in the numerator and you drag it down to the denominator, it becomes a positive exponent. And vice versa. If you have, for example, let's say 1 over x to the negative 2. So now we have our negative exponent in the denominator. But if I drag it across my magic eraser of my fraction bar to the top, you get a positive x squared in the numerator, and they're actually the same thing. So then looking at x to the 8th over x to the 10th, if we subtracted, that would be x to the 8th minus 10, or x to the negative 2. But again, I can't have that. So if we look at our expansion, or our expanded form, so many x's. And I simplify. Remember, anything divided by itself is 1. I'm left with 1 in the numerator and then x squared in the denominator, which goes right along with our idea that if x to the power of negative 2 has this negative exponent in the numerator, I would need to drag it down to the bottom. So our negative power rule, and I'm just going to skip to the actual rule itself, a to the power of negative m is equal to 1 over the power of a to the m, and vice versa. So we're going to look at 1, 2, and 3. And there's kind of a way to just ignore the negatives in a sense if you think of it like the shortcut I was telling you guys about. So we'll do the long way first, and then we'll do the shortcut. When I'm dividing my same bases, that's when I subtract the exponents. So a to the power of 2 minus 3, and then b to the power of 9 minus 3. So I get a to the negative 1, and then b to the 6th. But right now I have this negative exponent, and it's seemingly in the numerator of a fraction. So I need to drag it down across my magic eraser, and I'm going to get b to the 6th over a positive a to the power of 1. Because remember, if it's a negative exponent in the top, you bring it down to the denominator. And if it's negative in the denominator, you bring it to the top. I want you to make sure that you're understanding I'm not saying something like 2 over negative 3a to the negative 4. While yes, this has the negative exponent and would need to move, this negative coefficient does not need to move because it does not have a negative exponent. The only thing that you're going to move across the fraction bar are going to be your negative exponents. So this would actually become 2a to the positive 4 over negative 3. And then this would be okay, just like that. So let's try 2 on our own. Go ahead and pause the video. Actually, really quick, we're going to go and look at the shortcut. When you look at your a's, the denominator has more a's, so a goes to the denominator, and it has 1 more, so the exponent stays 1. And the numerator has more b's, and it has 6 more, so you'd put it in the numerator with the exponent of 6, which is exactly what we got down here. So now take a moment to pause the video and attempt number 2 and number 3 on your own. When you're ready to check your work, unpause the video to see how you guys did. All right, how did we do? Hope we did really well, you guys, and this is the end of our lesson. If you need any help, please don't hesitate to reach out to me or Mrs. Garcia